Okay, so physicists at the time were totally confused. They had no clue what was going on because it was so different than what they expected, based on classical physics. So they needed somebody who kind of thinks or thought, outside the box. You've heard that before, right? Well, that's Einstein, Notice he's a bicycle rider. All right, anyway, so what did Einstein say? Einstein said, light comes in chunks. And the energy of a chunk is hf. H is called Planck's constant. It's a super incredibly small number. I think we learned that a couple of chapters ago. But anyway, E equals hf. Now remember, V equals f lambda, but we put c for speed of light. So therefore, F equals c over lambda. So instead of saying equals hf, you can also say E equals hc over lambda. A lot of times we use this because when you talk about light, you generally know the wavelength, not the frequency. But sometimes we'll use this too. Okay, so what's a chunk? A chunk of light comes in chunks. A chunk is called a photon. Sometimes we say, a photon is a particle of light. That doesn't sound very good, but that's okay, I guess, we say it. Okay, so light comes in chunks. A chunk is called a photon. All right, so that's Einstein. Well, so what? Whoopee. Okay. Also, he said that every photon travels in a straight line. Gee, where did you hear that before? The ray model of light, right? Okay. Now wait a second. You got to think about this equation. This equation is totally ridiculous. Energy. We think of it's a particle of light, right? It's a chunk of energy. So that's a particle, right? Particle. But wait a second. There's a wavelength in the formula. So we're saying that light acts like a particle and a wave. Now that's ridiculous, but it's true. Remember we talked a lot about this when we talked about the wave theory of light? I kept saying particles and waves are completely different. Remember that? Well, sorry. Here we have an example where a photon acts like a particle and acts like a wave at the same time. Weird. But it's how it is. We'll talk more about this, don't worry. Remember that? I showed you this a whole bunch of times, right? Remember I told you that we were going to explain. All right. So particles and waves are completely different. Well, all right. Okay. All right. Now, so light comes in chunks. Chunk is called a photon. The photons can't be divided. So there's no such thing as a half a photon or 1.5 photons or anything like that. And that's not such a big deal. I think of a piece of dirt. You have a piece of dirt. Can you have a half a piece of dirt? No, it's a piece of dirt, right? Okay. So photons are emitted and absorbed on an all or nothing basis. That means that something can absorb like one photon or two photons, or three photons, but you can't absorb like 2.5 photons because it doesn't make any sense, right? Okay. All right? Okay. Let's see. And we're going to see how these explain the data. Just hold on. All right. The energy of one chunk or one photon is delivered to one electron, okay? So that means when the photon is absorbed by the metal, all of that energy gets absorbed by the single electron. Okay, so you say, whoopee! Well, let's see how this actually explains the data, all right? Okay, so here we go. Let's see how it does it. So first, let's just talk about this. We'll get that later, all right? Just let's talk about this, okay? Okay, so, increasing the light intensity increases the current. Well, no kidding. I sort of said this already, right? If you increase the light intensity, what are you doing? You're getting more photons per second. If you're getting more photons per second, that means that you're emitting more electrons, right, per second. So, that's not a big deal. That was the easy one, all right? So this makes sense. It's not a big deal. It made sense classically, not a big deal. We'll get to that later, I promise. Okay, let's talk about this. There's a threshold frequency that depends on the cathode material. Okay, let's talk about that. Okay, remember, an electron is emitted if the energy of the light is greater than the work function. Is greater than the work function, right? Because the light, remember, the energy of the photon is absorbed by the electron. If the electron has enough energy, if it's greater than the work function, it's ejected. Okay, so the electron is emitted if the energy of the light is greater than the work function. All right, well, okay, what's the energy of light? HF. Okay, and again, that has to be, okay, so HF has to be greater than E0. So let's find the threshold frequency, right? The threshold frequency. So let's do this. To find a threshold, we're just going to say that, put a little 0 there. And that means that F0 equals E0 over H. Okay? So if the frequency is greater than that, if the frequency is greater than that, the electron is going to be ejected. So this is called the threshold frequency. Wow, there it is. Okay. So, again, classically it doesn't make any sense at all, but this makes sense when you look at Einstein's model of a photon having energy equal to HF. Okay? So, if the frequency is greater than this threshold, F0, the electrons are gone. Well, that's cool, because, classical physics couldn't explain that threshold frequency. Now, regardless of the light intensity, the current appears instantly with no delay. Well, come on. It either has enough energy or it doesn't. If it has enough energy, why is there a delay? It doesn't have to wait to get, the metal doesn't have to wait to get hot enough, right? We're not talking about temperature at all. We're just saying if the light has the right energy, in other words, the right frequency, the electron is emitted. Okay? Now, let's do something which is going to be a review from electricity. Okay? Hold on a second. Oh, yeah, let's talk about, not yet. Okay, let's talk about this V-stop. All right, the V-stop. So V-stop has nothing to do with the intensity of light. Okay, so here we go. So V-stop. Well, what did we learn about, it's a voltage, right? And so way back when, we learned that a voltage is equal to kinetic energy over E. Remember that? The electron volt, right? All right, so V-stop equals the maximum kinetic energy divided by the electron, right? The electron charge. And why is it maximum kinetic energy? Because remember, we have the metal there, the electrons are going this way. This is going to be negative, that's going to be positive, So this is going to stop, right? And this is connected to the battery and all that. So when you get this voltage large enough, it's going to stop even the fastest electrons, right? Even the maximum kinetic energy, they're not going to reach that because this is so negative and this is so positive. Okay, so V-stop is maximum kinetic energy divided by the charge of an electron. All right, now, what is this maximum kinetic energy, Well, it's just the energy of the electron minus the work function. Agree? Because that's going to be the maximum kinetic energy, The electron has some energy, but first of all, it has to, give up or exceed that work function, and then anything left is going to be the kinetic energy. So we just have that. Now let's use our Einstein formulas, right? What's the energy of the electron? Well, it's the energy of the photon, right? Because remember, the electron absorbs all the energy of the photon. So that's just HF. And what's E0? I just erased it. HF0, we divide by E. And then you know, this is the only, I mean, these are all, everything is a constant except for the F, right? Let's write it differently. Let's write H over E F minus H F0. Remember, this is V stop. So look at that equation. It's an equation of a straight line, right? You know, Y equals mx, you know, plus or minus b, because this is a constant, right? This is a constant. This is a variable. You know, that's what you're plotting, right? So there should be a straight line. If this is right, if Einstein's right, you plot v stop versus f. You should get a straight line, right? That's what the prediction is. So that's the equation. And look, v stop only depends on the frequency. There's nothing here about intensity, right? Intensity is completely irrelevant. The v stop only depends on the frequency, you know? And of course, this, right? All right, so look at that. So this is data, okay? This is data. And what does it look like? Straight line, right? Straight line. Yeah, I should have made mine down here because it's a negative intercept, right? Yeah. Okay, so Einstein's prediction was shown to be correct. So that's awesome, totally awesome. All right, so there you go. All of the experimental results that confused people at the time were explained by Einstein's model. And as I told you last time with relativity, Einstein received the Nobel Prize for the photoelectric effect because it was so important to show that classical physics was incorrect. All right, finally, you have a question for you. Okay, a xenon arc lamp is covered with a filter that only transmits light 400 nanometer wavelength. When the transmitted light strikes a metal surface, so this is the photoelectric effect, a stream of electrons emerges from the metal. If the intensity of the light striking the surface is doubled, what happens? So please pause your video and figure it out. All right. So look, we're not changing the frequency. All we're doing is changing the intensity. The intensity is the number of photons per second, right? Bright light has a lot of photons. Dim light has a small number of photons, you know, per second. Okay, so if all you're doing is increasing the intensity, you're getting more photons, so that means you're going to get more electrons, right? And so, you know, you get more electrons are emitted in a given time interval. Okay, that's okay. That makes sense. All right. Now here's a cooler question. A xenon arc lamp is covered with a filter that transmits only 400 nanometer wavelength light. When the transmitted light strikes the metal surface, a stream of electrons again emerges from the metal. All right, now here's the new part. The filter is then replaced with one transmitting at 300 nanometers. And the lamp is adjusted so that the intensity of the light striking the surface is the same as it was for the 400 nanometer light. With the 300 nanometer light, what's going on? So pause your video and answer the question. I'll give you a nice big hint. There's your hint. So figure it out. All right, this is it. When the wavelength gets smaller and smaller, this gets larger and larger, so the energy gets larger and larger, right? So all it means is that since the photons are going to have more energy than they did when they were 400 nanometers long, right, the wavelength, so it just means that the electrons which are emitted are going to be more energetic. That's all. Just that formula. Okay, let's kind of just pause and review. All right, let's just review. So the particle model, which is like, what's a particle of light? It's a quantum chunk of energy, you know? And let's talk about waves and things like that. Okay, so Einstein, light comes in chunks. Incredible, important formula equals HF, which is H over lambda. Again, H is incredibly small, right? And so, you know, the energy of a single photon is incredibly small. And that's why it took people so long to figure out that it acted like a particle, because it's so, so, so small. A chunk of light is called a photon, or a chunk of energy called a photon, whatever you want to call it. The chunks, photons, can't be divided. The energy of one photon is delivered to one electron. Okay, and this all agrees with the data, you know? So this is low intensity light, and you can see that each one of these is a photon, okay? It's a photon impact on a screen or something like that. So low intensity light is detected as specks, okay? And you know what? We can measure these specks. We can detect them. We use something called a photomultiplier tube, a PMT, to detect single photons. And guess what? These PMTs use the photoelectric effect to detect single photons. So a photon comes in, and an electron is ejected and amplified, and you get an electronic signal. I have a couple of these in one of my labs. So, I mean, they've been used for a long, long time. They detect single photons. So that's the particle-like nature of light, okay? Light acts like particles, right? It sure does, you know? Light acts like particles, photoelectric effect. On the other hand, you know, light acts like waves. And this is just review. You do the double slit experiment with waves. I can't believe I said that. You do the double slit experiment with light. If you have, remember that? And you get an interference pattern. And so here you go. So you're doing this experiment with light. You start off with dim light. You see these, you know, photons, right? You can do it, just wait longer, wait longer, wait longer, wait longer. And what are you starting to see? A pattern, right? And so when you do the double slit experiment with enough light, you know, a large number of photons, you see an interference pattern. So you see that the photons, you know, they act like particles and they act like waves, which is completely weird, but it's true. And I talked about this before, so I'm not going to talk about it again. This is the single photon experiment, where the single photon went here and recombined here, and by moving one of the mirrors you can get constructive interference and destructive interference. I mean, it just shows that the single photon emitted by the molecule acted like waves. We talked about that before. So, what's the conclusion? What's light? Is it a particle or a wave? Well, both. It's kind of crazy, right? Sometimes it acts like a particle, sometimes it acts like a wave. You need both models. That's how it is. Okay, yeah, all right. So, we already talked about the ray model a long time ago. I don't want to talk about that. Just, you know, with lenses and mirrors and all that, light travels in a straight line. And just to reiterate this for the millionth time, photon model, light is made of massless photons. Massless. So they travel at the speed of light. Anything that has mass has to travel slower than the speed of light. Okay, light's made of massless photons, travel in a straight line, speed of light, in a vacuum, right? In a vacuum. Energy of photon equals HF, H over lambda. This is the cool one. The superposition of a large number of photons has the characteristics of a classical wave, right? You do the double slit with a large number of photons, and you see an interference pattern. That's what that means. Okay? The addition, or whatever you want to call it, of a large number of photons has the characteristics of a classical wave. You get an interference pattern when you do the double slit experiment. Okay, now, this isn't a book, that's why I'm talking about it. So sometimes we okay, so this is energy, and this is position, right? So sometimes we visualize a photon as something called a wave packet, okay? So it's supposed to be the wavelength, you know? It's just a classical model. It's wrong, all right? It's wrong, but we're going to use it later on. So that's the only reason I'm mentioning it now, right? It's just a kind of a classical, you know, trying to use classical physics to describe a photon, okay? So you see that the energy is, you know, it varies and the position varies and it has a wavelength. Again, it's just all garbage, but it's a model, and we'll use it later. So I'm just want to show you that now. All right, so that's strange, right? Light acts like a particle and a wave, and I kept trying to convince you when we did waves that particles and waves are completely different, right? I mean, come on. A particle, you know, it's at one location, it has a mass, right? And particles don't go through one another. Waves, they go through one another. You know, they're spread out. You really can't say, what's a mass of a wave? It doesn't make any sense. A wave is a disturbance, right? So I really tried hard to convince you a long time ago when we did waves that particles and waves are completely different. And I did it on purpose because I wanted you to be shocked when we got to light. So now we see light acts like a wave, acts like a particle. Completely weird. Okay, let's get even weirder. So this is a French scientist, de Broglie. So he was a theoretical physicist, right? Didn't do experiments, just thought a lot, all right? So this is what he thought. He said, well, golly, so I'm exaggerating, right? But anyway, he said, well, golly, if light, you know, which certainly has wave-like characteristics, if it also behaves like a particle, well then, he said, all particles should act like waves. Whoa. All right, you get that? Light acts like a wave, but also acts like a particle. Therefore, all particles, you know, like electrons and protons, particles with mass, they should also act like waves. Now that's weird. Okay, he didn't stop. He said, and here is what the wavelength of a particle should be. What? The wavelength of a particle? Yeah. So this is the famous de Broglie relationship, which was shown to be correct. So the wavelength of an electron or a proton or a buckyball or whatever equals this Planck's constant, which is a super small number. That's why we don't, well, you'll see, over the mass of the particle times the speed of the particle. So that's a de Broglie wavelength, incredibly important. And again, this equation is totally crazy, but it's true. Because here you have a particle, right? Mass, come on. I mean, mass, that's particle property. But then you have wavelength, wave property. So in one little equation, you have particle and wave. Crazy, but it's true. It agrees with experiment. All right, now, so de Broglie, when he was thinking about all of this, he hadn't received his PhD yet. And so he put this and his thoughts, you know, about particles and waves in his PhD dissertation. And he handed it in to his committee, and his PhD committee kind of said, man, what are we going to do with this? You know, because it was kind of a radical idea, right? And so what they did, they sent it to Einstein, and Einstein gave it the thumbs up. So it's kind of funny. All right, now let's calculate some of these wavelengths, okay? Oh yeah, I just want to keep rubbing that in, right? Okay, so here's Usain Bolt, pretty fast fellow, right? Let's calculate his wavelength. How do you do that? Let's do it. So remember, lambda equals h over p, which is h over mv. Okay? So h, 6.63 times 10 minus 34 joule seconds, pretty small, don't you say? Okay, I'm just going to guess for his mass. I have no idea what his mass is, but I'm just going to say 66 kilograms. And let's say he's going kind of slow for him, 10 meters per second. So you work that out, and it's about equal to 10 to minus 36 meters. Well, good golly. I mean, come on. That's ridiculous, right? A nucleus is 10 to minus 12 or something like that. So this is, this is too small to measure. We can't measure that, all right? Way too small. All right, so forget about Usain Bolt. Let's do a very fast electron. So we have this thing called a free electron laser. You can make that out. Right? It's a big laser. And then you have very, very fast electrons. Let's see what the wavelength is for a very, very fast electron. Okay, so lambda equals h over p, h over mv. So h is there, mass of electron. 9.11 times 10 minus 31 kilograms. Okay, let's just say it's going at the speed of light. Now, it's not going at the speed of light, right? Nothing that has mass can go at the speed of light. But let's just say it's going like 99.999999 times the speed of light. Well, that's the speed of light, as far as I'm concerned, right? So 3 times 10 to the 8th meters per second. Okay, you do that, you get 2.4 times 10 minus 12 meters. Easily measured. You know, now we're talking about atomic and nuclear distances. So what am I saying? I'm saying that if you have a fast electron, you can actually measure its wavelength. It's insane, right? You can do it. Okay, you say, aha, prove it. Prove it. What do you mean you can measure the wavelength? Well, gee, if an electron has a wavelength, if it acts like a wave, you should be able to do the double slit experiment, right? Get an interference pattern, right? Yeah, well, let's do it. Okay, so double slit with electrons. Well, you notice at first, you know, you just see the specks where the electrons land, no pattern. You wait a longer time, uh-oh, what's happening here? See a pattern. You wait long enough. What do you see? You see an interference pattern. This is from electrons. An interference pattern, which is a wave characteristic, right? I mean, again, let me just beat this to death. Here's the screen. Here's the double slit. Okay, if the electrons acted like a particle, you'd see a bunch. You see something here, you see something here, and that's all you would see. But what's happening? The electrons acting like a wave, right? So you see this interference pattern. So there you go. That's proof, right? That electrons act like waves. Crazy, but it's true. Okay, let's see. Oh yeah, this is even cooler. All right, so this is, okay. Let's just read this. With a weak With a weak electron beam, we can send one electron at a time through the apparatus, through the double slit apparatus, and still observe an interference in the resulting pattern of electrons. Now, if that's not insane, I don't know what is. I mean, think about it. One electron at a time, and you're going to get an interference pattern. Well, how can that be? I mean, what's it interfering with? Itself? No, the point is that the electron acts like a wave, right? And so you have to think of it like that. The electron acts like a wave. So you're not just having one electron go through the double slit. You're having the electrons acting like a wave, and the entire wave is going through the both slits. And that's how you're getting an interference pattern. This is true. And it doesn't matter how long you wait. In other words, you could shoot one electron, wait 10 minutes, shoot another electron, wait 10 minutes. Eventually, after a long time, you're going to actually see an interference pattern. Now that's crazy, but it's true. Okay, and that is hold on a second. Yeah, that's a good place to quit. Let's quit.